introduction. So could you please introduce yourself and talk a little bit about your background?
Yeah, okay. Sergey, thank you for giving me this opportunity. My name is Thorsten Last. I am the Director of Development and Engineering at Origin Quantum Systems. And pretty much what I am is I'm experimentalist by virtue or by education. And well, what to say about it is my journey to this point, I think, was not fully linear, or maybe it was, because what I always wanted to understand is, and to be part of, was the extension of Moore's law. What is needed and where are we and what could come next? And pretty much I started my career in Germany, in Bochum, moved then to the Netherlands, to Groningen. But what I figured out across this time span that a traditional academic career or environment is not would help me in this decision-making process. So I decided early on not to pursue a traditional academic career. But in short, I'm always interested in the physics of nano devices and how these nano devices could affect Moore's law. Well, and that's pretty much all I did up to this point. We can go in very much detail in all of these, but maybe what is also interesting to say, experimental physics was my starting point, but then I moved on the path towards a role which is called system engineer. And now my role is system engineering and, of course, director of development and engineering at Orange Quantum Systems.
Yeah, and I have a lot of questions which I would like to ask you. And I guess my first question will be, or the first topic which I would like to cover is Dutch quantum ecosystem. Oh. And I would like to ask you, what do you think happened in the past in the ecosystem, where we're standing right now, and where we are going with quantum ecosystem?
Oh, it's actually very okay. These are quite a few, and please interrupt me because it's a threefold question. I think coming back to my also early career, I was drawn to the Dutch ecosystem actually from the start. I was aware that they had a strong commitment in basic science on understanding the physics of quantum transport, or well, they kind of found quantum dot behavior and understood it very nicely. And pretty much I was drawn very early on towards this ecosystem in itself. Pretty much 10 years ago, working for Bart van Wees in Groningen.
And when do you think it started? Like when we actually can say that there is an ecosystem, right?
Okay. Well, I think the scientific one was very early on established because what I think happens here, but that's my personal view, as compared to Germany, for instance, the universities themselves were always quite well equipped here, because in Germany, for instance, you have the basic universities for education, but then you have the Max Planck Institutes for fundamental research and the Fraunhofer, which has a strong network of institutes across Germany for the applied sciences. Whereas here in the Netherlands, the universities did a wide range of different aspects, or covered a wide range. And that was already a good starting point, that in these good universities in Amsterdam, Delft, Eindhoven, Groningen, and others, that this kind of basic science ecosystem was already there. 5 years ago, specifically in Delft, based on scientific discoveries across the line, which we could go into, but I would quickly name that silicon became another kind of interesting aspect in quantum technology, or circuit quantum electrodynamics was discovered, that this and the transmon in superconducting research. These kind of discoveries helped technology development, and technology development was kind of now accelerated 5 years ago by the setting up of QTech here in Delft. And well, QCEFT is something else, but I can mostly talk for, well, since I'm an experimentalist, I'm very much aware of what's going on here. And TNO and TU Delft came together to form a research center, which is called QTech, and that is in recognition of that there is something in it, the potential for quantum technology. And now we are 5 years later, and what we see now, the first prototyping results are coming out of this ecosystem, small ecosystem. And well, the first steps, and that's why you are talking to me, also commercialization. What I mean with ecosystem, I think it's also a dynamic system. So my thinking on the Dutch national agenda, and please interrupt me also again, is what we have the chance is to increase the ecosystem, to kind of increase the cake, or how, I mean, pretty much what drives me also personally is what we have the chance with for the next steps here in this phase is that we have the chance to build some sort of a new industry.
Yes, yes. And now actually it was a big news a couple of weeks ago, I don't know, maybe a month, that a Dutch quantum ecosystem get quite a large funding. So what do you think about this new funding and where we are going with this money, let's say?
Well, it provides us with the potential to make the next step. It's kind of in recognition, but also gives us now the opportunity to kind of extend beyond basic research and invite also other contributors of society to actually make it sustainable and pretty much I'm a very pragmatic person. I want to have a high-tech commercial sector here in the Randstad in Delft with let's say people get educated at the University of Delft. They should not go right away to ASML. They should not necessarily go to the US, even though the US is great. I spent 6 years of my life there. I love every bit of it. But having also a strong engineering base here is what, wow, it's my personal view, but it would thrive me to build this up, to help there.
And actually, when we're talking about, let's say, ecosystem and the main focus of this ecosystem, there is maybe a naive belief, I'm not sure if you will agree with that pretty much the main focus of the ecosystem is superconducting qubits and basing and growing the quantum computer based on superconducting qubits. Do you think it is a correct statement?
No, I would kind of challenge this view. To some extent, in my opinion, the transistor of the quantum era has not been found yet. And there are quite a few indications that maybe we need a diverse set of solutions out there. And where is this superconducting view coming from? Well, I think it's not completely surprising when you and I are both in this Technical University Delft environment, which I already highlighted. Quantum transport was always very much core and center. So what electrons are doing in nano devices was studied for many decades. And that is a very normal thing. However, there is also a very strong community actually in Germany or in Austria who actually pursue a different path on ion trap technology and has very strong support and is considered currently one of the, on a similar growth path. And actually, in fact, that prototypes in 19-inch racks of small-scale quantum computing demonstrators, I think, are almost ready for sale from the ion trap community. So in conclusion is there are currently front runners, and now I can use my system engineering background again. I define certain technology readiness to these individual platforms. And I agree with you that the edge currently has the superconducting ones. And actually, this is good because we learn not only about the devices themselves, but also a lot how the interaction between the devices and the higher components of the stack function. And that it actually can be translated to other platforms. So, meaning that to bring this a little bit concrete, I think what we should not do is fully focus on a single horse, but we should make use of the current state, what we have, and then very much carefully investigate the differences, but also then detect the commonalities between these different platforms. To give you one example, I think arbitrary waveform generators are being used for controlling transmons as well as spin qubits, and actually also ion trap systems, I think. Mm-hmm. And so pretty much there is, we are at an early stage where certain standardization aspects, well, have to be established. And then you will see that actually that superconducting ones is a good starting point, but might not be in 10 years from now, or comes to a certain end where a new discoveries come to kind of supersede this kind of system.
Yeah, and let's say if you want to speculate a little bit about different quantum platforms, what's your favorite and why? Let's say because I think right now the most of the progress is focused on superconductors and of course ions. Right now, in my naive perspective, I would call them leaders. But what do you think is really like the best platforms and what, let's say, the dark horse somewhere?
Yeah, so I'm not trying to fall into this trap. I still very much, I give you another example where I think you can derive certain similarities from. ASML is selling lithography machines. For many decades, the UV systems were the kind of, well, the high-end systems, and they are still a large portion of their sales at this point in time. Well, just 2 years ago, they kind of finalized the development of the initial versions of EUV. And pretty much what you see is that deep UV was there, is still there, and will be there for a long time. And EUV will, kind of carve out its own niche or market. And I think the same kind of applies here when I would say to currently focus a bit on the superconducting side is good, but not necessarily because the superconducting ones are superior, but you can also learn a lot about the interaction between a quantum system and medium-sized quantum system of, now up to 50 to 100 qubits, and how it's kind of translated in controlling it. And I think you will find a lot of learnings there, and therefore it should be also considered as a good starting platform. You should not wait for this magical qubit, which has extremely long coherence times, and it can be still very nicely controlled and fast controlled. You can do something in between with these platforms which are currently available.
Yeah, so, and pretty much what you're saying that we still have to do a lot of research, and I completely agree with that. But now, for me, there is an interesting question how, let's say, we're talking about the interaction between academia and industry, right? Because when we're talking about research, we always assume, maybe naively, that, okay, research could be done in academia, but now we want to build a quantum industry. So how do you see, in your eyes, what's the interaction between academia, let's say, and industry?
It's a good one. That's also what we try to learn, how to make this happen in our concrete Dutch national agenda. I think what is required, I mean, both sides have to recognize their value, and what you see is that R&D is definitely needed. And so I don't see kind of either or decision making, but collaboration and co-development I consider very much key. And what I think about is, for instance, there are certain aspects of a full stack which have high technology readiness. They can be very much, these components can be very much procured and established, and then from these kind of high tier L components, interfaces have to be well defined. But for instance, on the other side, there is the quantum chip, whether it is a spin qubit system or a transmon system or a trap for ions, I think. And what is the best architecture and topography to build these chips? Or even it's a hybrid solution between semiconductor and superconductor solution. I mean, all these kind of things have to be played out, in my opinion, in the scientific environment. And there a lot of contributions can be made. So meaning that if I envision that collaboration is that system integration of certain aspects of high TRL combined with bright ideas from the scientific community on the other side could then build this kind of full stack with the best people in mind. So like you need system integrators, you need certain component providers, and they have to be interacting closely with each other and define the interfaces very clearly. And that's what I'm stating regularly, also in other settings.
Yeah, and I fully agree with this idea, and it is a very nice proposal. So when I think, I'm coming from scientific background, and when you work in the scientific group, the main, let's say, outcome of your work is scientific paper, right? It's most of the time. But now we're talking about industry, so now we have to produce results, or at least some sort of, not tools, not advice, not devices, but something, let's say, tangible, right? And now I think it might be a problem changing the mind of scientists, so they don't need to produce just a paper, but they have to do some sort of development, like really industry related. What do you think about it? Do you agree with this?
I think I would say this black and white view was there a decade ago, I think, because as I said, I mean, what I started to sketch out is that also the Dutch technology ecosystem moved from basic sciences to recognition that for instance, applied science providers like TNO have to be involved towards now prototyping. So, and to give you to come back to the superconducting community, actually, they recognized very early on that when they had their transmon qubit operational, let's say in 2008, 2010, they wanted to, they learned the ways of system engineering, and that's why you kind of now have these. You were asking me whether this is the real thing, the superconductor, or just currently a snapshot of time. But this is what happens when also within this, let's say, public research environment, recognition is there that organization and careful analysis and interaction of individual parts, lead to progress. And the next phase, of course, will become when I talk about prototyping or commercialization, that also we have to learn, well, coming back to the interfaces, because we have now timelines which we should adhere to, because we want to satisfy a customer at a certain point of time. And now we have to accomplish certain things which we in the academic environment might have a year or two time, or 2 PhD students time. Well, we have to accelerate this. And pretty much Orange Quantum Systems, that's one of the core offerings and thinkings behind Orange Quantum System, is that we can help accelerating the research on quantum physics and the development of quantum technology for quantum computing. So that's kind of the mindset which is shifting, and well, hopefully our value proposition also will be listened to.
Yeah, and actually now while we're talking about this subject, I would like to ask you about the QTech, and especially how the QTech position itself, because let's say when I'm thinking about superconducting qubits, the two big names pop up. It's let's say Google and IBM, and right now I'm thinking about the QTech. So what's the position of the QTech, and what's the vision for this organization, I would say?
First of all, I mean, you're asking somebody a question who is not currently working at QTech, right?
Okay.
That's my role is Director of Development and Engineering at Orange Quantum Systems. What I can, let's say, from the outside is QTech is very much a faculty in the Technical University of Delft, supported by TNO to some extent. What that means is I would not necessarily link this entity to kind of commercial groups or publicly traded companies like Intel or IBM. It's a different entity with a different goal, I think.
Yeah, so what you're saying, we cannot really compare, let's say, IBM and QTech, because there are actually the mission or the goals of these companies is kind of different, because QTech is rather a faculty at the university and IBM is a like company, proper company, right?
Exactly. So the main I think what you should keep in mind, QTech is not a company, and it's not. Yeah, it's pretty much it's a conglomerate of different ideas how to move forward quantum computing R&D efforts or quantum internet efforts, which I think that's what I want
But
to say.
Still QTech is focused to build a quantum computer, but it wouldn't be, let's say, a commercial quantum computer. It will be more for the, let's say, testing and research, right?
So first of all, interesting. I suppose we want to, and that's the thing. They have a lot to offer, and yes, quantum computing is one of the key drivers behind QTech. But the rat race, in some respect, as is being paid out between companies, this is not their incentive. I think what is pretty clear, what many PIs are after is also to learn how to build the fault tolerance into this quantum computing systems. And that, of course, is not necessarily compatible with near-term, let's say, business advantage. It will pay off in the long run, but the near-term business advantage is highly likely not in pursuing research into fault-tolerant quantum computing.
Yeah, and actually now when we're talking about the quantum computers as a proper computer, so what do you think we can do with quantum computers? Maybe it's a bit of speculation, of course. So especially in the era of noisy intermediate scale quantum computers. So what do you think we can expect from these computers?
Yeah. Okay. Now we go to the zoom out phase.
Yeah.
First of all, we need to what we have to learn in some respects now in the Netherlands or in Europe, also to build machines of 50 to 100 qubits. That's from the hardware perspective the core exercise, and there I stated how it could look like by how extremely good scientists and commercial entities like Orange Quantum Systems could bridge the gap and build together in co-development manner the system. What it can be done, of course, should become a computer and it should solve differential equations, maybe fluid dynamic solutions. So pretty much people learn now for the first time to deal with these many qubit systems, what to do with it. And is there currently a quantum advantage? No. But I think what is required, we have to move beyond the demonstrator phase, and it is recognized, for instance, that variational algorithms are kind of a way forward to kind of get deeper into real applications, I would call it. We have, for instance, partners or part of the ecosystem is also very much contributed to looking for use cases like the Leiden University around Benaker or QSoft, of course, in Amsterdam, or there's even a startup in Amsterdam which is called Q&Co, and they provide input for these hardware manufacturers like us. And in this combination, we are trying to kind of design systems in the future, which then, offer on the one hand the idea solutions and compute real questions, but well, my personal view is also to keep it still in a phase that we have the universal quantum computing in the long run. So the complexity comes in when we look too closely into a business advantage at this point in time, but neglect a bit the universality where the power actually lies. And this kind of interplay between these kind of aspects and I agree, the lack of a clear, simple business case makes it challenging, but I think there is enough in this sphere which provides input. For instance, component providers will sell components to these mid-sized systems. That will happen. People need arbitrary waveform generators or require cabling or need lasers or fridges. So this is the market in itself. And then we need to learn how use cases can be built efficiently with reduced amounts of qubits, or how to handle noisy qubits. And of course, what is also interesting, the chip manufacturing, I think will, in my opinion, and that is where I'm looking positively into the future, I think it will improve. Because currently, why are they noisy is also that most of the chip manufacturing at this point in time is very much in academic shared facilities. Is pretty much people from Intel or TSMC would get red faces if they would see how somebody would build a 10 qubit transmon chip here in Kafli. Even Kafli is a very nice scientific environment, but so this will also give a boost to improved chips, reduced errors, and will provide us also on a next path, I think.
Yeah, so if I understand you correctly, what you're saying that we're still early in a stage of developing quantum computers, and I fully agree with that. And now it's a question, let's say, what should happen, what development we really require, because the billion-dollar question is when it happened, right? So when these practical questions become available. So what should happen? So is it like we simply have to gradually improve our technology, or we're waiting for, let's say, some sort of opening mind development? So what in your perspective is the main challenge here?
So and that's what I also earlier said. In my opinion, we should start working now on things which are available and should not wait, because then at the end, the community which is waiting might have missed the boat at that point in time. So because we can learn a lot of, well, let's put it this way. I personally learned a lot to be actually part of the team who was building Quantum Inspire last and brought it to the public, and which is a quantum computing demonstrator in the cloud built at QTech. And we learned a lot about how the interaction at these different layers of the system functions. And now we pursue it, and hopefully we find solutions to build larger systems and how to control them and effectively make use of them. And only that brings us then to the certain readiness that we can jump on this train when something happened. Because at the end of the day, what it comes down to is what we discuss very bilaterally right now. It's many things from different sides have to come together. And what is obvious at this point in time, that we have a large group of people who look what could be done from the use case perspective, from the algorithm perspective. There are component providers, but what still is lacking is, there are challenges out there. One of them I already addressed, that chip manufacturing has to improve, right? Has to be moved out of standard academic environments. That is one of the core facilities. But there is also the interplay between hardware and software to control these quantum systems, to make them, let's say, make these experiments, spectroscopy, and at the end tune up a sizable quantum chip. That was taught by Google in some way, but I think there is still a lot of to be gained, how to keep really control and make it ready for computation. And these kind of things require a lot of resources in software engineering and a good interplay between the quantum plane and the software. And yeah, there's a lot to be done still next to the chip manufacturing. And so we are at the early stage, while it's already ongoing, the early stage, but there is momentum that in this complex system, people now or entities find their layers. And now we kind of more and more discuss interfaces between these layers, which is good. And the acceleration of R&D efforts will take place in that respect.
Yeah, yeah, and I fully understand that right now we're early in a stage of developing quantum computers, but do you maybe feel at least the interest from some, let's say, companies, let's say banking? I've heard maybe this news are not correct that, let's say, IBM AMRO would be interesting in finance or maybe others. So do you feel that there is at least some interest from the companies, or they're kind of approaching you in somehow?
Well, me personally, it's not the focus of Orange Quantum Systems. That comes down to the point is they also need a point of entry. And the point of entry lies for them usually at the algorithm side, because they want to do something with it. That brings me back to my argument. If you are looking at me, and no offense, if I would be a monolithic quantum computing R&D setup provider, which now is out there in Europe, also in the US, then I would be the point of contact with for Shell. However, what I think is at least what would fit better, at least in the European ecosystem, is a more collaborative effort as well. Here, what we put forward, or I put forward as an argument, there are, for instance, coming back to ASML. ASML didn't build its EUV machine not on its own, but they are partnering up with two big companies in Germany, Carl Zeiss and Trumpf Laser. And these three have recognition, are independent companies on their own, but they three defined their interfaces as such that they are able to build together an EUV machine. So bringing me now, my personal focus is system integration and working towards the readiness of a quantum computing stack. I would rather invite somebody a little higher in the stack. I would name Q&Co or Leiden researchers to then see the potential of the system I'm helping to build for the actual end user. And so meaning that this conversation, which is not easy to make if you have some person who is expert in programming, needs to exactly define the spec requirements for a chip. These are now examples why it's moving, why it's tricky. It's exactly these conversations. People have different skill sets, and we have to learn to talk to each other to make it most efficient. It's actually, it boils down to the fact that now a quantum computing R&D system seems to be too complex for a single entity or single person to control and to understand. That's actually the basic of it. And now we need to try to learn different languages, or need to understand carefully one another and define the interfaces where their contribution is essential to make it a better system.
Yeah. And now when we're talking, let's say, about the full stack or the full ecosystem, could you talk a little bit about Orange Quantum Systems? What's the vision? How did you start it?
Yeah, okay. So yeah, you put me on the spot with QTech. Yes, so I cannot deny it. I'm coming out of QTech, and so there is no denying. But as I already earlier mentioned, I'm not a spokesman. So please, it would be good for you maybe to invite somebody from QTech at some point in time. But yeah, QTech was kind of when moving out of this technology development phase, and we kind of were launching Quantum Inspire last year. We thought we have lots of components together to think about that there might be a community out there who wants to have on an accelerated pace also gaining this, such a system for learning how to actually get into this field. And so pretty much our perception is that Orange Quantum System, based on the IP and knowledge we built up over the years, we can accelerate this research in quantum physics and development of quantum computing technology. And what we concretely offer for R&D labs is customized characterization and calibration software. So pretty much you are still at the university, maybe you have to code in your experiment. We have solutions to make it much faster for you. Develop customized full stack setups for R&D into quantum computing. And that is pretty much by the twofold approach is we have software packages to tune up qubits. The biggest portion of packages we have now for the tune-up of transmit qubits. And pretty much next to that, we offer system design and system engineering practices for those of you who want to build complex R&D setups. And pretty much that leads to an acceleration of R&D efforts for the customer and the cycles. So pretty much very concretely, we finished a 16-week project with our partners where we defined this approach with independent companies with clear interfaces that we were able to kind of build a full stack system in TNO based on a lab, which we proved to, we wanted to prove that we can set it up as a team of independent companies in a way that it will be ready for experiments. And we provided from week 13 to 16 that we can tune up a transmon qubit performing spectroscopy experiments, coherent qubit control, and simple quantum gate analysis and device calibration and automation. So pretty much we designed the whole system, wiring, components in the room temperature control circuit with our partners, and then even showed by validation through experiment that this can be actually done. And yeah, that's one of the core examples where Orange Quantum Systems can help the ecosystem to move forward at a much more accelerated pace, because what I hear in, what becomes important, and that's also more a personal view, is we have to find, coming back to our national agenda here, also in the Netherlands or in Europe, is time is not standing still. We have in the global market, we don't have only Google or IBM, but recently there was some news nobody knows a lot about, but in China, activities are ongoing on a 62 transmon qubit chip. People are also eager to see what's going on there. So pretty much, I think we need to find ways and to accelerate certain activities to prove that we are also still on the edge of what is possible in a in-time manner, I would call it, and not in 6 years or 8 years from now, but pretty much now. And yeah, Orange Quantum Systems wants to help them.
Yeah, and maybe can I address the project which you just described, which was developed at TNO, at TU Delft. So you said in 16 weeks you built the full system, but by the full system you mean like a quantum computer?
A single qubit system. It's not a quantum computer because we made hard decisions, hard choices, not to, for instance, make a perfect shielding, and secondly, avoid tuning up a 2-qubit gate. Because that is coming back to more professional way of working. We have timelines. Let's say we have available some facility for 3 months or 4 months, and then we need to max out what is possible. And what you will see is it's still an incredibly fast way of building such a system, and kind of it proved that it's possible, and we can build now, well, towards the 2-qubit system. That's our plan actually in the next few months for another session. So scaling is still now possible, but this is now kind of a good kind of exercise where we set up a project start, a project end, and in between we had to design, procure, assemble and integrate and validate by experiment, then the last month, that this is possible. And we decided at the beginning that it will be single qubit tune-up. It was still very challenging because the other part which we had to let go is optimal shielding, which is usually taking a lot of effort and a lot of thinking and months of kind of fine-tuning of the right packs so that you package everything perfectly. We had to make I would call it shortcuts, which is not perfectly designed, but we ended up with in-spec results. Just to give you an idea, we wanted to have T1s of 10 microseconds, and the T1 of this qubit was 15 microseconds. So.
And you said 16 weeks.
Yes.
Okay, and it was, and just for my curiosity, how many people were working on this? Because it seems like outstanding results. In 16 weeks, you delivered, let's say, okay, single qubit. Okay, I understand there are short corners, but okay, so how many people working on this?
Well, the Delft ecosystem is now comprised of a number of companies, which with their individual strength. That's exactly it. If at a certain point in time we needed, for instance, people who provide us, let's say Delft Circuits, had to provide us with cabling and filtering. And yeah, that was being done in a timely manner, provided in, it was a deadline in January where the wires had to be ready. Same thing holds for Q-blocks. They provide arbitrary waveform generators and knowledge on room temperature control electronics. And Orange Quantum Systems brought, for instance, the knowledge of system integration and implementing the experiments to the table. And if we define our interfaces very neatly, then there are, then these resources can be channeled. So it's not that full-time 20, 30 people were standing around the lab. That was not even allowed due to Corona measures, of course. We built it within Corona times, according to Corona measures, but we put it into different subsystems and defined the interfaces clearly and had initially agreed as a joint venture on the outcome, on the goal of this project. It was clear that we wanted to have a single qubit tune-up with certain numbers of T1 or T2 star. And from that, we derived the timelines and what has to be done. And then said, okay, well, coming back to the shielding, let's make it simpler. But on the other hand, maybe this is sufficient. And yeah, it proved the right choices.
Yeah, it's outstanding results. It's really looks good. And my last question would be about the time scale and timeline. So let's say, of course, it's a speculation. I understand that it's very hard to make real predictions. But if you think, let's say, about 5 years and 10 years, what will happen with the quantum market and quantum industry?
Yeah. So what I sense now is I'm focusing here on Europe. National agendas are being set up. The next phase probably will happen that these individual national agendas will be hopefully properly linked. And then that in 5 years from now, we have definitely a base of these mid-scale quantum computing systems at our disposal, where concrete business questions can be addressed. And we should also be a little bit patient in this respect, because it is a new industry, it is a new technology, and it is acknowledged already that we need to have many different players working in concert. Is actually it's already an important recognition, and from that on, I think we will have more quantum computing systems out there, which people will make use of.
Yeah. I think it's a good point to finish our discussion, and I would like to thank you for your time and efforts for joining me today.
It was very interesting. Thank you, Sergey.